We're going to talk about types of forces today and start to identify them and figure out how we find out their size and how we find out their direction, because forces are a vector, so they have a size and a direction. And we're going to start with weight. And weight is the mass times the local value of g. And mostly it's going to be, we're going to think of it as down in the minus j hat direction is how we're going to usually label this. So on Earth, g is 9.8. If you go to a different planet, a little hard to do these days, then you would have a different value of g. And m again is your mass. That's measured in kilograms. And so if we look at weight, the direction, so this is the size, so that's the magnitude, that's the size or magnitude, and the direction is down. So if I have an object that's sitting, so a block here that's sitting, I draw the force as down, and I say this is my force mg, or in your book you'll see this as a W for weight. Okay, this is the force due to the gravitational pull of the Earth on us. Okay, and so in MKS units, those are measured in newtons. In imperial units, those are pounds. So we're used to pounds, but we can convert between pounds and newtons. Okay. The next force that we're going to talk about is kind of a tricky one. It's called the normal force, and your book is going to refer to it as a capital N. I tend to use force sub N because otherwise you get confused about newtons. But the normal force is a force that's perpendicular or normal to a surface. So here's my surface. It's always going to be perpendicular to the surface. So if my surface is like that, it's up. If my surface is like this, then that's going to be pointing, in this case, on this side towards me. On the other side of the plexiglass, it's going to be towards the camera. Okay? An easy way to find the direction on the normal force is to put your hand on the, the base of your hand on the surface, and your thumb will point in the direction of the normal. So I put it there. If I have a curved surface, then notice my normal points out from there. So that's my normal force. That's the direction. It's perpendicular to the surface. The size is tricky. The size depends. It just depends. It depends on what's needed to support things. So if you think about a floor, it can support you, and hopefully it can support you and your roommate. But when you aren't there, it's not providing that force to support you, okay? This tape, I've got this board sitting on a table, and when this board isn't on the table, if a puzzle is on the table, for example, then it doesn't have to support as much weight. So you can think of the normal force as sort of adjusting until it can't adjust anymore. You put something like an elephant on it and everything's going to fall through. I don't really have an elephant handy, so that's not a problem. But the size actually varies, and we'll see an example in just a minute. I want to do another force that's kind of like normal. It's called tension, and your book is going to use a T. I prefer an F sub T, and it is along a string. So if I've got a string or a rope, then tension would be, force tension would be along this direction. So it's always parallel to the rope, away from the object. So a long rope away from the object. And again, its size can depend as well. Often we know, because we know how hard whatever is on the end of this is pulling, like it's a person pulling with 10 newtons or something like that. But let me give you an example of how these kind of work together. So if I have this block and I have a string on it so that I can pull up with it with some force, but I pull up with a force so that it's not quite lifting off the table. So let's say its weight its mg is 10 newtons down. So that would be my mg value. And let's say the tension force along this rope, it's not quite as long, force tension, let's say that's 8 newtons. And if this block is not falling through the table and it's not accelerating up or down, then there must be another force that's supporting it. And so that force that's supporting it is from the table is a force normal that's equal to 2 newtons. And if this tension force goes up to 10 newtons, then I don't have a normal force anymore. The floor hasn't changed, it just doesn't have to provide the force anymore. So the floor can adjust as it needs to. If you want to think about the floor as a little bit like a trampoline, it can bend slightly, right? It flexes. It depends on the floor, whether it's sort of a squishy trampoline type floor or a much stiffer floor. So it can bend. If we take this force tension up to 11 newtons though, then what's going to happen is this is going to start accelerating up, right? Because I'll have, instead of 8 newtons here, I'll have 11 compared to my 10. I'll have an excess force up, and that will give me an acceleration. And in this case, because it was at rest, that acceleration does tell me my velocity is going to increase, and it's going to increase up. Probably what will happen is often when I lift things, right, I accelerate them when I first lift them, and then because they're going at a constant speed, I provide, in this case my hand provides a normal force going up for the marker, and so often I just provide, my hand provides exactly enough force to balance out the weight. Okay, so you could call this a hand force, or if you really wanted to, a normal force off the hand. The semantics don't matter to me as much as, do you understand what's going on? So when I start it, right here, my hand force is equal to the weight. When I get it started, my hand force is a little bigger than the weight, but now if I move with a constant speed, my hand force is back to equaling the weight. Okay, and so this is how we start to understand these forces. We're going to run into, in chapter 6, frictional forces. And then later on in chapter 7, I think we're going to look at spring forces. I'll just mention spring force briefly. So spring force, just for completeness, is minus kx, where this is what's called the spring constant, and x is how far you've stretched the spring, and it's in the minus direction because the spring always wants to pull you back. So this is the spring force. Okay, but what we're going to do is really focus on these forces to start with, and then we'll add in friction and then the spring, because they get more complicated as we go along.